and that is rotational kinetic energy. So of course we've met kinetic energy before. It's the energy associated with motion. Now, in the context that we met it before, it was the motion of one whole object, one whole body. And in translational world, we said that objects move as a whole. All right? Each point on an object moves in the same way and the same distance at the same speed. But now we have objects that are rotating. Okay? Well, you can imagine then that, I don't know, for some reason in my head I like this example where you attach a ball to a string. So this ball is attached to a string, and you kind of chuck it, and so it's going to be forced to go in a circle. Well, certainly this ball is in motion, but just because it's going in a circle doesn't mean its kinetic energy is zero, even though it sort of starts and ends at the same point. We could calculate a kinetic energy that's associated with the motion of this ball. And it's not incredibly difficult to do, as long as we know a few things. So the first thing we need to know, of course, is the angular speed of the ball moving about this axis of rotation. And we need to know the distance from the axis of rotation to the ball. And we just need to realize that those things are related to the tangential speed. All these things we've been talking about the past day. Okay? And so if I use those quantities, I could come up with an equation for the rotational kinetic energy, which is just, starting with our basic definition, 1/2 times the mass of the object times the speed squared. Nothing new here. It's just now I have this v sub t in this case because it's a tangential velocity. But you realize, though, that v sub t is related to omega. It's related by r, by the radius. So I get 1/2 mass times the radius omega squared. And if I go one step further, and by one step I mean move the parentheses over a little bit, I get a quantity that looks really, really kind of similar to my normal kinetic energy definition. There was a 1/2, there's a term that has mass in it, and then there's this speed term. So this is like 1/2 mass-ish term times velocity squared. So what we do as physicists, we say, well, this kind of looks, this kind of looks like a modified mass term. We should call that something, so that we can write this equation so that it looks almost identical to our kinetic energy term, just with rotational quantities. So we assign this thing an I, a capital I. And that's not impulse, which is why sometimes impulse is written as J. This I thing is like a modified mass. And I've sort of hinted at what this concept is before, but it's called the rotational inertia. All right? Now remember, in translational world, mass was inertia. Inertia and mass are the same thing. Remember, inertia is just a resistance, the ability of an object to resist a force. Okay? Well, in rotational world, now we have rotational inertia. It doesn't get a special name like mass, but it's clearly dependent on mass. It's equal to mass, but there's a distance dependence, like all things when we're talking about rotations. So rotational inertia, is just the rotational analog to mass. That's all it is. Just like we have angular velocity is the rotational analog to velocity, rotational inertia is the rotational analog to mass. And I'll point out, I usually call this rotational inertia. I don't know why, but you'll also see this referred to as the moment of inertia. That's inertia. No, I was right. Inertia. All right, so both of those concepts or both of those names are referred to. So you'll see, I think in the book it uses moment of inertia. I like rotational inertia better. All right, so we have this rotational analog to mass. The problem is it's not only dependent on mass, it's also dependent on some distance. And if you look really closely, you know, we came up with this relationship, I is equal to mr squared, you know, because of our specific problem. But you can imagine a different problem, right? So you can imagine instead of having one ball attached to a string, you have many balls or something like that. And so, well, now, you know, there's many masses. There's mass 1, there's mass 2, there's mass 3, mass 4. And these don't necessarily need to be the same distances. You can have R1, R2, R3, and R4. And so the question is, well, how do you calculate, you know, what is the moment of inertia for this system? I could go through the same process to calculate my kinetic energy, but if these things are all fixed, each object has the same angular speed. So if I wanted to calculate the kinetic energy, it's equal to 1/2 I omega squared, I just need to come up with some total rotational inertia. Just like if I was calculating the translational kinetic energy, if this thing were just translating, I wouldn't go through the process of calculating 1/2 mv squared for each object. I might just add the masses together and then multiply those by the velocity squared. So this is something that we have to do in rotational world, is oftentimes we have to come up with, we have to solve for I of the system. We have to solve for the rotational inertia of the system. In a system like this, where we have these discrete objects, like individual objects at different locations, in order to come up with the actual rotational inertia, it's actually pretty straightforward. We just add them together. So m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. And if you like math, that's kind of a long thing to write, so we could just stick this summation symbol in the front and do a summation over I of mass I r I squared. So this is usually how you'll see this written. All right? For I objects or something like that. Where I goes, in this problem, goes from 1 to 4. So that's how we calculate the moment of inertia. If you have discrete objects like this, you just add up the individual moment of inertia, and you get the total. And then you can plug that into your equation for the kinetic energy, multiply 1/2 times omega squared, and you get the kinetic energy. But there seems to be, if you think about it, though, there's a difference between these are I call these discrete objects. You know, they're just points, they're masses. They're not related to one another, other than that they're connected by these rods or whatever. But what about something like continuous objects? You know, and for example, what do I mean by that? Well, what about like a hoop? You can imagine like a metal hoop that's rotating. And you know, let's say it's rotating about this axis. You know, so it's coming into and out of the page. You know, we'd want to calculate the moment of inertia. If we want to figure out the kinetic energy of that thing while it's rotating, we need to calculate the moment of inertia. But there's not these discrete masses that it can add up really nicely. So how do I handle that? Well, I actually do. In order to be able to handle this, I do have to treat it as discrete masses. So I have to break this up into chunks, where this chunk is like mass 1, this chunk is mass 2, this chunk is mass 3, that chunk is mass 4, et cetera, et cetera, et cetera, all the way around. And then I can use the same equation. So I is equal to the sum over I m sub I times r sub I squared. You know, but the interesting thing is I'm going to get a different answer depending on how I break these masses up. So what I really want to do is I want to make those masses really, really small. And if I do that, what I really end up doing is I'm taking an integral. And I'm not going to write this down because you don't see this in this course, but it looks something like this. So if you took Physics 223, you would have to deal with this problem. Now, obviously, we don't solve this here. And this is a little bit tricky. This is kind of a tricky integral because you probably have never integrated over something that wasn't a dimension like x, y, or z. So handling this is a little bit tricky. But that's how we really solve for these continuous masses, continuous objects. The good news is we don't have to do this because instead we use, somebody else has done it for you. So we're going to use table 10-1 in your book. All right? So, for a lot of different objects that are, sort of standard shape, like rings or cylinders or spheres, we could calculate the moment of inertia, but it's been done. And so you can just sort of look it up. And so if you're doing a problem and you encounter an object of some, sort of not too crazy shape, chances are you go look in your book and you'll find a moment of inertia for that object. And it'll be based on its mass and its radius, or some characteristic length. All right. But I just want to, again, I want to re-emphasize the difference between, the moment of inertia is the same for a continuous object or these discrete sort of objects. For these guys, we can't really do the calculation. We rely on a table in a book. Okay, but if you have these discrete objects, then yeah, you're going to have to do the calculation by adding up each individual component. All right, so that's enough about kinetic energy. Now let's actually take a look at how to use it. So a couple examples I want to do today. Let's start with the most basic one. And that example is simply a ball that's rolling. About as simple as you can get. So you have a ball radius 10 centimeters. And it's rolling and has a speed of 1.41 meters per second and a mass of 1.2 kilograms. Actually, this is a disk, not a ball. So it's not a sphere, it's a disk, it's flat. So I want to ask the question, what is the kinetic energy of the disk? And I will be kind and provide you with the moment of inertia, which you could look up in your book. The moment of inertia for a disk is just 1/2 mr squared, mass times the radius of the disk. So tell me, how would I calculate the kinetic energy? Radius is 10 centimeters. Sorry, it's a little small. Leah, did you say something? 1/2 I omega squared. W is work. Is this right? Does everybody agree with that? Yeah? I only see a couple of people nodding. Why don't you other people agree? Casey, why don't you agree? Shane? You agree? Jane, what about you? You're quiet. You just had that gigantic coffee. You got to be like hopped up.
Sure, I agree.
You agree? I think that's wrong. Who can tell me why it's wrong? Don't look at your notes. Use your brain.
Do you have to substitute like I in for the mr squared? And then,
Well, okay, yeah. I mean, I gave you I, so you'd substitute that in. But that's what I'm saying is you're missing. There's something missing here. We could put that in there. That's given. But there's something else missing. Jukes, what's up? Velocity, what? Velocity squared, so like this? No, I'm asking what I want you to tell me. I want you to be clear. You have the right idea, or you're at least saying the right thing. Danielle, what were you going to say?
The tangential velocity.
Again, so what, this?
No. Could you substitute
No substituting.
W for no? Never mind.
You could totally do that. You could totally substitute that in. And we're going to do that. What? Here? That's the same thing, isn't it?
So
Isn't that the same thing?
Substitute the W out for the tangential velocity divided by the radius.
Well, I could do that. I could do that, but that's not changing anything. It's the same value. Omega is equal to V divided by R. That's absolutely true, but you get the same answer if I gave you omega or if, either way. So this thing is rolling. Do you remember what rolling motion is? This is the rotational kinetic energy. That assumes this thing is just rotating. But it's also translating. There you go. I knew it was in there somewhere. So you have to add in the translational kinetic energy. So this is a total kinetic energy. All right? We have a new type of energy. You can add it to the list of potential, gravitational potential, elastic potential, kinetic, translational kinetic, and now rotational kinetic. So when we do a conservation of energy problem in a couple seconds, you get to take into account, a new type of energy. So this is really what we're doing. Okay, so we need to substitute an I. We don't know what omega is, but we do know, as Danielle said, that that's related to the velocity and the radius. So I can go ahead and start to substitute things in. We got 1/2 mr squared here. Omega is just V tangential, which actually isn't tangential in this case, because again, this is translating. It's just this V. It's the velocity of the center of mass here. V squared over R squared, plus 1/2 mass times velocity squared.
Why the velocity?
Because this is squared.
Oh.
So I cancel out these R squareds, and I'm left with 1/4 mv squared plus 1/2 mv squared. All right, so that's what I'm actually looking at now. I've got this extra, extra term that's half of the actual overall kinetic energy. All right, so I can plug in some numbers. I get 1/4 times the mass is 1.2 kilos. The speed is 1.41 meters per second. I got to square that, plus 1/2. I should have just combined these two terms. 1.41 meters per second squared. And if you run those numbers, you should get a total kinetic energy of 1.79 joules. Okay? So since this thing is since this is rolling, it's both translational and rotational kinetic energy. All right? Now let me take a second and talk about why we didn't. So Danielle was saying, and I think a couple of people said that we could write this omega. We usually write this as equal to, or I guess how I've been writing it is V tangential is equal to omega times R. But we define V tangential as being like this speed up here, which should be very long. Right? So why didn't I use why didn't I use this V sub t and I just used this V here?
Because isn't the speed of the wheel equal to the speed of the Wouldn't it, why would it be different?
Why would it be different?
Why would it be different if it's like on the top of the wheel and then
Well, okay, the way that I've drawn this picture, remember in a rolling motion, the speed here is 0, right? But when we're talking about the rotational kinetic energy, we're separating out the rotational component from this picture. So I'm treating, this part of the motion is just, this part of the kinetic energy is just the spinning. This part is just the translating. So I am talking about the tangential speed here, but these two pictures are different. In this picture, the velocity of the center right here is 0. Sorry, this is very small. Pretty small. Yeah, so the velocity of the center of the wheel, if it's just rotating, is 0, which means the velocity of the rim is 1.41, because I've separated out the rotational aspect. And then I'm just adding that to this translational aspect where all points move at the same speed. Okay? I want to make sure that's perfectly clear because it seems a little odd that I'm choosing the speed of the center of the wheel when we're always talking about this tangential speed and relating that to omega. Chooks, question? Sure. Let me go down and write a slightly larger picture. Okay? I drew this yesterday, and so I'll draw it again today. I'll do it backwards, though. So what I have here is rolling motion. So velocity, the speed at the bottom of the rim where it's in contact with the ground, that speed is 0. In the middle of the hub, this is like the speed at which the thing is actually moving as a whole. We'll just call that like a v sub w, v whole. Okay? And then what's the speed at the top? Right, it's got to be double. So this is 2vw, which we tend to call, usually we'd call this like the tangential speed. But that's only when this whole thing is rotating. But this thing is not just rotating, it's also translating. All right, so what I'm doing up here, what I was just trying to show you was that this picture is the same as taking the rotational picture, separating the rotational picture and adding it to just the translational picture. All right? The translational picture is really easy. All points of the wheel are moving at the same speed. All right, in terms of these quantities, what is the speed of what is the speed over here? Is it 0? Probably not. VW or 2VW? Right. All right. The length of these lines, these arrows, is VW. Okay? But if I just look at the rotational picture now, so again, I'm separating that out from this rolling motion picture, what I have is the velocity up on the top of the wheel is v sub w. The velocity right here is vw in the other direction. And then the speed here is 0. Okay? So this is what we've done. When we've added together, to get our kinetic energy, when we've added together the rotational component plus the translational component, I'm really adding together two different pictures. And so I have to recognize that this VW in this picture, in other words, the V that goes with my rotational kinetic energy term, is actually the V that's assigned to the center of my wheel. Okay? Just like I've drawn in this picture. And you can even do the math here. If you add the top points of both wheels, you get VW plus VW, that's 2VW. VW plus 0 is VW, and then VW minus VW is 0 down here. All right, so the picture is consistent. Yeah, this one is pointing to the left, so if you're adding them together, right. That's correct. Does that make a little bit more sense? All right, I'm trying to avoid any confusion when you're working problems about, how to define this velocity, how these velocities compare. All right, and we're looking at, again, we're sort of taking this and we're breaking it up into two separate pictures and making a relationship between the velocities on the rim versus the velocities in the center from each of the pictures and how they relate to one another. So you have to sort of be able to see that to make those connections. Okay, so that's rolling motion part A. All right, let's do rolling motion part B. So now instead of just having a ball rolling, let's add in a little bit of complexity. And we'll put a ball on a ramp. Okay, so you have a ball of radius r, and I think I'll give that to you in a little bit. And it starts 2 meters off the ground. So this thing is going to roll down this ramp. till it gets just to the bottom of the ramp and then it goes away. And I want to know, what is the speed of the ball? All right, it starts from rest. Come on, do it. There we go. So the ball starts from rest. So I'm asking again, what is the final speed of the ball? Okay, give you a couple things. Let me tell you that the angle of this ramp is 30 degrees. And that's all we'll give you. All right, so in this case, we have the ball is rolling. There's no friction. Slowing it down anyway, and there's no slipping. I guess this is really no air resistance. There has to be friction or else it would slip. So this is kind of wrong. I guess there is friction, and it's the reason that the ball is actually rolling. Okay, no slipping. So let me ask this question. What types of energy are going to come into play here? So this is a conservation of energy problem. We have some initial energy stored at the top that's converted into a different type of energy at the bottom. What types of energy do we have to take into account? Kinetic? All right, so gravitational, kinetic, but don't forget now that we have two types of kinetic energy. We have kinetic energy translational and kinetic energy rotational, or if you want to call it total, that's fine too. So we have to account for the energy that goes into rolling. This thing initially isn't moving. So what we're going to do here is we're going to take all of its energy is initially stored in gravitational potential energy. That's going to get transferred into translational energy and rotational energy. All right, so this is a conservation of energy problem. We have no work done by an external force. So if the initial energy is equal to the final energy. If I write down all of my terms, I have initial gravitational potential plus translational kinetic energy plus rotational kinetic energy. And these are all initials. That's got to be equal to the final gravitational potential energy plus the translational kinetic energy plus the rotational kinetic energy. Okay? I'm free to make all sorts of definitions here, so I'm going to say that height is 0 at this point. That means that my final kinetic energy is going to go to 0. And we know that this thing is starting from rest, so my initial kinetic energy terms both go away. All right, I hope that you're getting good at doing this sort of thing, maybe not in the context of rotational yet, but in your latest homework assignment, you should be getting good at crossing out terms and setting up coordinate axes so that you get other terms to go away. So I'm just left with the initial gravitational potential energy goes into translational and rotational kinetic energy. So I can write down the equation here. I know gravitational potential energy is just mgh. And then my final kinetic energy is 1/2 mv squared plus 1/2 I omega squared. Okay? Once again, I know that V is related to omega by R for the same reason we just talked about in the previous example. And then this is a ball, so you could go ahead and look up the moment of inertia for the ball. And it's equal to 2/5 times the mass times the radius squared. And so if we plug those values in, we get mgh is equal to 1/2 mv squared plus 1/2 times 2/5 m r squared times v squared over r squared because of the omega term. And once again, my r's are canceled out. Okay? Now, since all terms have mass in them, the mass goes away. And you'll remember this from problems when we were doing inclined planes before. The mass didn't matter when you're dealing with inclined planes, at least most of the time. Okay? And so now I can rearrange all these things and I can solve for the final speed. So I'll do final speed squared. That looks like it's equal to, I'm going to factor out some things first. So the final speed squared, there's a 1/2 here, and there's a 1/2, that becomes a 1/5, and that's equal to GH. All right, so what I get is V squared is equal to 10/7 times GH, strange number. But this becomes 7/10, and then I move it to the other side, so you get 10/7. Or V is equal to the square root of 10 divided by 7 times G times H. And if you plug in G is 9.8 and H is 2 meters, you get 5.3 meters per second. Okay, so that's interesting. Now, what's more interesting is, let me ask you this question. Do you think that that velocity is smaller than, less than, greater than, or equal to the velocity of a similarly massed object that wasn't rolling? All right, so let's say instead of having the ball rolling down the hill, you replace the ball with a block that has the same exact mass. It slides down the hill like so, no rolling. Do you think the final speed of the block is less than, greater than, or equal to the final speed of the ball? Less than. Why? Okay, so what I think I heard there was you have energy going into, you're causing it to spin. You're causing this thing to spin, which means you're giving it some of the energy that you have, some of the initial gravitational potential energy has to go into that spinning, as opposed to just the speed of the block. So it goes faster. And you can verify that doing if we do a quick jaunt from this equation, we don't have rotational kinetic energy, so this just ends up being like so for the block. So if I solve for V, that's equal to the square root of 2 times G times H. All right? So this number is going to be greater than that number, because 10 divided by 7 is less than 2. All right, so we're going to we're going to put all of our conservation of energy, work energy theorem to test now, and start to look at another problem involving a more realistic pulley. So our pulleys up until this point have been massless, and as you may or may not know, massless pulleys do not exist. So we're going to be a little bit more realistic. We're going to take a problem that we've seen before without the pulley and just stick the proper pulley in there. So we've got these two masses. One is suspended vertically. We're going to release these things from rest and figure out what the final speed is as this guy goes down here. It's going to hit the ground at some speed. V final. What is that? That's what we're after. Okay? So this is a conservation of energy problem. What is the first equation that I'm going to write? EI equals EF. Is this correct? Whenever I ask that, it's obviously the answer is no. I got to figure out a better way to phrase that.
No.
Why is that not correct?
Because there are external forces acting.
There are external forces. There's friction, because I say if the coefficient of kinetic friction is 0.35, what is the final speed? So what we're really dealing with here is there is a difference in the mechanical energy terms, and that's going to be equal to the work due to friction. All right, so we're throwing in the extra wrinkle of having some friction in there. All right, so what I can do to write what I'm really looking at here is there's going to be some change in, I don't know, potential energy. If I add that to the change in translational kinetic energy, and I add that to the change in rotational kinetic energy, that will be equal to the work done by friction. So this is the equation that I'm really solving. And all I have to do is plug in all the terms that I don't know. So I've written these all as deltas, so that means I'm taking finals, subtracting them from initials. So let's just go through it and go crazy. All right? Yeah, Chooks? How's that? Oh, but I need more room to write. Okay, I'm going to postulate that this thing is not going to change height, which means I don't care about the gravitational potential energy of it. So delta UG sub 1 is equal to 0, because it's not changing height. So this doesn't change, its potential energy doesn't change, so I'm not going to care about that. This guy, yep, changes height, so gravitational potential energy will change. They both change speed, and this thing's going to rotate. So all the other terms are going to have something. All right, so I'm going to write it down. Gravitational potential energy, I only care about block number 1. So I have mgh final minus mgh initial. I add that, I'm sorry, this is block 2. This is mass 2, mass 2. I add that to the kinetic energy. Let's do the translational of mass 1, 1/2 m1 v1 initial squared. And then I subtract that from the final. Minus 1/2 m1 v1 initial squared. I need to do the same thing for block 2. So I add 1/2 mass 2.
Wait, aren't those two the same thing?
Aren't what the same?
V1 initial squared minus. Didn't we say change
Sorry?
potential energy is 0?
Final. I said the change in the potential energy of mass 1 is 0.
Okay, so that.
Absolutely, this is not 0. This is going from here to here, so that's not 0.
Using block, that was for block 2 right there?
Yep. So this is mass 2, mass 2. Okay. This is mass 1 and mass 1. Then I'm going to add the change in kinetic energy due to mass 2. So this is V2 final squared minus 1/2 mass 2 V2 initial squared. And then I need to add, scroll. I need to add the change in rotational kinetic energy. So I have 1/2 I omega final squared minus 1/2 I omega initial squared. That's equal to the work done by friction, which is mu sub k times the normal force, which if you do the free body diagram, you will realize is m times g times delta x. All right, it's a big, ugly equation. It's all 3 lines. Luckily, a few things are going to go away and a few things are going to be related. So let's first start off by saying, how does VF1 relate to VF2? All right. These things are connected by this line, so they're going to be, as they move together as one, so that means they're going to be equal to one another. So the final velocity of block 1 is equal to the final velocity of block 2. The other thing you might notice is that there's an h here and there's a distance here, delta x. So delta x is the distance that this thing moves until it's in its final position, something like that. And you should realize, since we've done this sort of problem before, that as I've written it, delta x is equal to h. All right, I'm free to choose one of these two h's. So I've called, basically the way that I've set this up, I've said that this is y equals to 0 and that this is at some height h. All right, by doing that, I'm saying that the initial position of mass 2 is 0. All right, nothing new here. You've done this before in a previous example. And then height final is h. And then all of my initial velocities are 0, because everything starts from rest, including omega. Okay, so a lot of things go away to make this at least a little bit simpler. So if I write down all the terms we have left over, it's m2 times g times h plus 1/2 mass 1 v1. Sorry, I'm just going to write it as v since v1 final is equal to v2 final. 1/2 mv1 v squared plus 1/2 m2 v squared plus 1/2 I omega squared is equal to mu sub k mass 1 times g times h. All right, that's what I'm left with. Yes, ma'am.
So for the first part, the delta, the changing in gravitational potential energy, is that for mass 2 doing the GHF, GHF?
Mass 2, yeah. Hard to see.
Why would the initial one be 0?
Because I can define h to be 0 wherever I want, just like we've talked about for the last week and a half.
Yeah, but I thought you just defined 0 at the bottom of the...
Oh, I did. Thank you. I'm sorry. You're right. You're right. That's what you're trying to tell me.
Yeah.
Okay, I did. I'm sorry. I went backwards, so that's right. My fault. I would have noticed that in a second when I had a funny minus sign missing. Thanks. That one's 0. Sorry. And then I'm left with, yes, a minus sign. Thank you. Okay, so there's my equation. And now it's just solving the thing. I mean, there's nothing else. There's no other physics here. The last thing I need to do is relate omega to v and plug in an I. So this thing is rotating. It's a cylinder. That's what I said the problem. It's a cylinder. It's going to rotate. And I know that v of the cable as it's passing over is the tangential velocity of my cylinder. So if I blow this picture up a little bit, it looks like this. So the tangential velocity right here, that's v. That's just the speed of the block. It's the speed of this cable as it moves over. Okay, so I can relate then omega, again, is equal to v divided by r, the radius of the pulley. And then if you look in your book, you can look up the moment of inertia of a pulley, of a cylindrical pulley like this. I forget off the top of my head what it is. It's just mr. mr squared. All right, so if I plug these two things in, what I get is minus m2gh plus 1/2 m1 times v squared plus 1/2 times m2 times v squared plus 1/2 times mr squared times v squared over r squared. And that's equal to mu sub k m1 gh. And I can cross out those two r squareds. And this is the mass of the pulley. Right? Now I just need to solve it for v, because that's what I'm looking for. So I've got 3 terms of the v's right here. I'm going to put those on the left-hand side and then move this term to the right-hand side and do some factoring. So I get a v squared 1/2 m1 plus 1/2 m2 plus 1/2 mp. That's equal to mu sub k m1 gh plus m2 gh. And I just caught a mistake. All right? This work due to friction term, we've dealt with work due to friction before in this sort of a problem. This term, should it be negative or positive? I made a mistake, so it should be negative. Now, why should it be negative? What's that, Leah? Because the force is opposing the displacement. All right. I think I knew what you're trying to say. So that should be negative because the force is to the right. I'm sorry, the force is to the left in our problem, and the displacement is to the right. So it should be negative. Okay, now I can go ahead and solve for v. So v is equal to the square root. These 2's are all just going to come to the top. And I'm going to factor out a gh. And I get m2 minus mu sub k m1 divided by m1 plus m2 plus mp end. All right, before I plug in numbers, I really like this problem because it's a complicated way to do a lot of stuff to get to the answer, and then you're left with this answer that's sort of ugly. And this is a really good time to take a look and try to, try to see if you can do that whole, hey, does your answer make sense? How do you look at this and ask yourself, does this make sense? You're like, I have no idea. I don't know what the answer should be. So this is sort of what physicists do, and this is what I hope you guys will learn throughout the rest of this class, is to look at this sort of thing and say, okay, if the total mass of the system goes up, what's going to happen to the velocity? Right? It sort of depends, right? If mass 2 just goes up, that's the one on the bottom, right? That's the one that's hanging down. That might be different than if the mass of the pulley goes up or mass 1 goes up, okay? So the denominator doesn't tell us a whole lot because it's too complicated. And then it's additionally complicated because of 2 terms up here on the top. But the top does tell us something. The numerator says that if mass 2 goes up, well, then the velocity's got to go up because the numerator gets larger. Likewise, if you get rid of friction, you get rid of this term, well, then the velocity goes up again because this term's negative. So at least by looking at the numerator, I'm sort of happy with this equation because it makes some physical sense. I know that if mass 2 is really, really heavy, it's going to move really, really fast. And I know if friction goes away, then the solution should go up as well. Right? So at least in terms of the numerator, I'm pretty happy. And then the denominator just says that the total mass is important. And that seems to make sense as well. I mean, all of the masses should certainly play a role. Right? So just looking at this equation, it's not immediately obvious right away that it makes sense, but if you do a little bit of thought, you could say, okay, yeah, I think that makes sense. You'd be really worried if you had these signs flipped. If this was positive and this was negative, that would say that friction was making it go faster, which that doesn't make sense. So that's a really good way to catch sign errors, if nothing else. Okay, so if we plug in some numbers, and I'll do that just so that you guys can see a solution. 2 times 9.8 meters per second squared. Height was 2 meters. Mass 2 was 7 kilograms. Minus 0.35 times 5 kilograms. And then I'm missing one of those. And that was divided by 7 plus 5 plus 2 kilograms. And if you do that, you should get an answer of 3.83 meters per second.